Hi, my name is Veljko. I'm an engineer here at Semaphore, and today I will be talking about ephemeral environments. In the past year or so, we went through a lot of changes in order to make our application open source. And one of those changes was an update of the testing process so that we can make sure our app runs on any environment our users might have. To start first with a bit of a backstory, Semaphore CI has been in the development or exists for about 10 years, and our infrastructure has evolved organically over that period. All of the app development we do, our configurations and testing procedures we have currently were set up with this specific infrastructure and our specific environment in mind. When the decision to go open source was made, it was clear that we will have to make changes in our code to decouple it from our own environment. And it was also clear this wouldn't be a one-time thing or a short-term effort. We would need to update our procedures to validate that each new version of the app we plan to release also work across all of the environments we claim to support. At that point in time, our CI/CD pipeline looks something like this. This is, of course, simplified a lot, but it captures the essence. Before I continue, I will share a few screenshots of our app, and I will use this opportunity to maybe showcase some of the functionalities our app has to offer, but I will do my best to not turn this into a sales pitch. So we are using the monorepo. In Semaphore, you can actually conditionally define which tasks or which parts of the pipeline will run, depending on which parts of the repo you updated. Here, I was working on a secret hub on one of our services, so we built only Docker image for that service, run tests for it, and perform some security scans. After that, we can trigger the promotion to deploy to pre-production or staging. After it works, or after we make sure it works as expected, we merge these changes onto the main branch, and after that, this deployment target or this promotion will become available as well, because you can deploy to production only from the main branch. The goal was to migrate to something like this. First part stays the same. Let's zoom into the rest of the pipeline. Now we want to package our app using Helm charts. After that, we want to spin up our test environment, meaning a completely new infrastructure, install the application there, and run end-to-end tests. These environments that are spun up on demand for the purpose of testing new version of code and then destroyed immediately after is what we refer to as ephemeral environments, and that's what I want to talk about in a bit more detail for the rest of this talk. So from the get-go, we knew we were going to use Terraform. It seemed like a best tool. We also use it already for our production and pre-production. But other than that, we weren't sure how to approach this. One idea was to separate it into three stages. Develop a Terraform for one of the ephemeral environments. Let's start maybe with the Kubernetes for Google. Once that is working, and we can deploy our app there, integrate it into our CI pipeline. And once that is working, use this first Terraform project to create a new one for another ephemeral environment. Maybe that can be Kubernetes for AWS. Let's start with this. I mentioned that we use Terraform, and we already use it to manage our Google infrastructure. Why not just use that one for spinning up this ephemeral environment as well? Well, it is bloated. We want to keep this one as simple as possible, so we don't have the need for all of the security things that are present in the production environment. We don't have a need for all of the redundancies. Also, this Terraform, which will dictate how the Google Kubernetes cluster actually looks, will be publicly available for anybody who wants to use. And we figured that other people will also appreciate simple setup that is cost effective more than something with a bunch of security rules that is made for production. On that topic, how much can we actually strip down from that starting point of a production Terraform we had? Turns out a lot. We have over 270 different resources in our Google, in our GCP. And for this ephemeral environment, we were able to boil it down to like 5, starting with the VPC, which automatically has default subnets for each region where Google operates, define a Google cluster, define a node pool, and also we need a way to store the certificates, the TLI certificates, so they can be easily referenced. And thankfully, there is a Google resource for that as well. We are now at 4 separate resources. Now we can put this on the side, try to install Semaphore using Helm on this fresh environment. It would look something like this. You can see that we need to pass some parameters that will be unique to each individual instance of Semaphore, one of them being the domain behind which it will run. And we should be able to see pods running within our node pool. Great. This is still not operational. We need something that will actually handle all the HTTP requests from the public internet, validate the HTTPS with the R certificate, and then route those requests to the destination services. Thankfully, Google offers something here as well. They have their own application load balancer, which we will use. The reason why it is here on the right and not on the left is because it won't be provisioned ahead of time. It will be created during the installation. How does it work? Once you actually run Helm install, a bunch of Kubernetes YAMLs are applied that will define all of the resources within the node pool. One of those resources is an ingress YAML, which defines all of the routing rules. If you put some of these annotations at the top of your ingress definition, Google Kubernetes engine will be able to pick them up, figure out that you actually want a load balancer Google's load balancer to actually implement all of those rules, and it will spin it up. Great. Now, this works as I just explained. And one more last reason why this still isn't enough, might be a bit unique to our own setup and the way we do installation. One of these pods is actually something we can call maybe an installation orchestrator. And during the installation process, this pod pings other services, initializes all the data that is necessary for the app to run properly. And one last thing it does is it tries to ping itself just to see if it is healthy, but it does not do it through the internal Kubernetes network. It uses a domain and the public internet to try to go through the load balancer. And once it can actually do that, the installation is marked as successful. So before we actually run the installation, we need to set up our DNS to point the domain we passed to our load balancer. But as some of you can probably see, I just mentioned that a load balancer is created or provisioned during this step here. So at this point in time, it does not exist yet. So how can we point our DNS to something that does not exist yet? We cannot, but there is this resource called the static IP within Google. You can reserve an IP address ahead of time during the infrastructure provisioning, point our DNS to that IP. There will be nothing behind the IP, but who cares? And now when we run our installation, we have to make sure that the load balancer actually attaches to this static IP, which can be done if we add one additional annotation saying we want you to use this static IP that we reserved. Great. Once that is done, Semaphore is successfully installed. We can test it and see that it's validated that it is working. First step complete. Second step, all of these things that I just mentioned, let's just turn them into a block of tasks that need to be executed within the CI pipeline. And that would look something like this. So the first part with Helm chart stay the same, end-to-end testers to run. This is what's new. We can zoom in here a bit and see that we are generating the certificates, then pulling the newly created Terraform code and using it to provision a clean Kubernetes on Google. After that's done, we are connecting to that Kubernetes, installing the newest version of our app, and also setting up the DNS. This here is a typo. This is a simple bash script, nothing to do with Terraform. One thing I want to point out, and then yet another feature I want to showcase is these blocks of code are executed on separate VMs. So here we are generating the certificate files, and here we need to use those files to actually upload them to Google. How can we do that? Well, before this job is done, it can upload the files to the artifacts, and this next job can just pull them and then do with them whatever it needs. The same thing works with the Helm charts. Once we created the newest Helm package, we upload it to the artifacts, and it can be easily pulled later here when we want to actually install that Helm app within our Kubernetes cluster. Great. Second part done as well. Now we only need to adapt this first Terraform to use AWS instead of Google. My thinking was, how hard can this be? How much difference can there be between GKE and EKS? They're supposed to do the same thing. Let's just use this Terraform, give it to any of the AI tools, tell it to adapt it for EKS, and the job done. This is what we have currently on GKE or GCP, and which works. I assume the EKS Terraform will look something like this, more or less the same, just different resource names. Turns out I couldn't be further from the truth. There are some trivial changes, like we are explicitly creating the subnets. EKS cluster cannot run just within one subnet. It needs two different. And after this is provisioned, we can try to install Helm using the same, try to install Semaphore using the same Helm command. Some of the pods are running, but I quickly noticed that none of the stateful sets are actually running. The reason behind that is, by default, on the freshly created Kubernetes cluster on AWS, you cannot claim persistent volumes. You actually need a separate add-on, and thankfully we can also create this or provision this add-on in the Terraform, but only when this add-on is part of the cluster, the pod can create persistent volume claims. Great, version 2, provision new cluster, run Helm install again. The stateful sets are working, but there are a bunch of other pods that are not being scheduled, as if there are not enough resources within this machine. But when I checked both the CPU and the RAM, we are nowhere near the limits of the node. So what can be the issue here? After a bit of research, it turns out one more difference between GCP and AWS is how they handle IP addresses. Google uses something they call IP alias, and they can assign how many of these. There is no limit to the number of these IP aliases per machine, so that does not limit the number of pods per machine. And on the other hand, AWS uses Elastic Network Interface, which, despite its name, doesn't have an elastic capacity. It caps it to around 50 or exactly 50 per disk machine type. And if you have some bigger machine, you can have like 100 pods running because 100 addresses can be assigned. We decided to, okay, we don't want to use a bigger machine. Let's just use two different machines and spread the load against across these two. And while I was researching this issue, I stumbled upon this Reddit post, which did make me feel a bit better because I wasn't obviously the only one with this problem. So we have now this like third or fourth version of our infrastructure. Let's try to install Helm in the same way. All the pods are running, but the load balancer is not being created. And if I go to the Amazon console or Amazon UI, I can see that the ingress resource has like green check mark. There are no issues with it. I also made sure to now include the annotation that is Amazon related and remove anything that is Google related, but still nothing. Turns out that the feature or the functionality that Google provides out of the box, where it monitors for the ingress changes and then based on those changes automatically spins up the load balancer, are not part of the EKS cluster, but there is there is a Kubernetes controller which you can install, which is just basically another pod within your cluster that will monitor for these ingress changes, and then it can create the load balancer. This here pod needs to be running before we start Helm install. So thankfully, again, we can use Terraform, and now Terraform, as soon as this cluster becomes available, attach to it and use Helm to install this ALB controller. It will also be present here on the right, of course. Now, when we perform Helm install, this one controller will be able to see that the new ingress is created. It will be able to see that we want Amazon load balancer, and it will then create a load balancer, which will work in the same way it does in the Google, at least in the same way as far as we are concerned. Now we are left with that last part. We need to set up DNS so that ping can actually work, or actually goes through the load balancer, and that will mark this installation as complete. I want to point out that at this point in time, I already spent like 3 or 4 days on a test I thought would take like 2 or 3 hours. I was just ready to wrap it up somehow and move to something else. So I'm thinking, again, this will be kind of simple, hopefully the last thing I need to do. Well, turns out Amazon's load balancer first doesn't have a static IP. They assign it some kind of DNS, and then behind the DNS is an IP address, which you cannot fetch and which changes over the time, so you cannot do anything with it. But can we at least now point this domain to that alias we received from the load balancer? Turns out no, because there is no way to know which alias it will get before it is created. And this concept of reserving the alias or static IP does not exist in AWS. Okay, at this point of time, I'm like thinking, let's try to move this here, so we can create load balancer and provision it before we start the installation process. That way, we will know which IP, or not IP, but DNS it has, and we'll be able to do this first step. And then afterwards, we just need some way to configure or to tell this controller, don't create a new load balancer. The one already exists, just attach to it. There is a way to do so. You can create a load balancer in the Terraform, and then if you match all of the tags from that load balancer to the annotations of the ingress, ALB controller will be able to match them and to use them. It's janky, but it works. The problem becomes when you want to do, the problem starts when you want to do a Helm upgrade, because if you update that ingress or any of those rules in the future and just perform Helm upgrade, will this ALB controller be able to update the load balancer because it does not own it, it's not created, or would you have to manually update the load balancer and then perform Helm upgrade? For this reason, this approach was out of the table. Thankfully, the third thing came up, and that is another controller, just like this one, called the external DNS. What it does, it listens for the moment when the load balancer is created, it fetches the alias that's assigned to it, and then it goes and updates the DNS, as far as, of course, you give it the permission to do so. So how do we work now? Basically, we do not need to set up the DNS. We just run Helm install, and we need to make sure that as part of our environment setup, we have these two controllers running. And then one controller will pick up the ingress change and create a load balancer. The other one will pick up the load balancer creation and actually update the DNS so that finally we can complete this ping and mark the installation as successful. One thing we needed to do is add one more annotation for the ingress, which tells this external DNS controller about the domain we plan to use. Voila, we are done. All 3 things are completed. We can finally call this migration to the new CI procedure done. It took me actually so long to implement this second ephemeral environment that one of the colleagues in the meantime already implemented the fourth one, or the third one, where we use a single VM. As a final note, it took like 30 minutes, or it takes around 13 minutes to provision everything for Google. About the same time, maybe a few minutes less for the AWS. It will come to no surprise that it takes less time to provision a single VM, but I was surprised how quicker it actually happens. It's around 40 or 45 seconds, together with like provisioning the VM, SSHing into it, installing the necessary binaries, including like K3S, which is a lightweight version of Kubernetes. So yeah, now we mostly use this ephemeral environment while we are working on a feature to validate it works. And then periodically, when we think that we implemented everything the way it should be, we can just once at the end run these two ephemeral environments and just validate that the newest version of the code works there as well. That has been it from me. I want to thank you for your attention and also thank you for attending the Semaphore Summit. If you have any questions, feel free to ask them on our Discord channel, and I'll try to answer as quick as I can. Thanks once again, and enjoy the following talk. Bye.
Hello everyone, my name is Damjan Becirovic and I am one of the engineers at Semaphore. In this session, we are going to take a deeper look at Plumber, the core component of Semaphore responsible for processing and orchestrating Semaphore pipelines. To start, let's take a look at the agenda for today's talk. Firstly, we are going to do a short intro through the main Semaphore concepts, which are pipelines, jobs, and agents. This part is intended for any listeners that are not yet too familiar with Semaphore. After that, we are going to take a zoom-out look to see what happens from the moment when you push your changes to your Git repository until your pipeline and jobs are running. And then finally, we are going to zoom in on the pipeline processing component, the Plumber service. We are going to examine the main principles and requirements that guided us in creating this system that is processing thousands of pipelines every day. We are going to look into the Plumber's architecture and examine the main points of its implementation. At the end, we will see how the system works on a simplified example and explore how we can extend it with new functionalities. So let's start with the first point of explaining the main Semaphore concepts. The rectangle that you can see in this image, called build and test, represents a Semaphore pipeline, which is an organizational unit that allows you to model your whole CI process. The pipeline consists of several blocks: setup, analyze code, and tests, which are, in this example, run sequentially one after another. The blocks can also run in parallel or depend on multiple blocks, which allow you to model complex use cases. The blocks consists of one or more jobs that are all run in parallel. A job is an executional unit that actually runs your tests and commands. Since we are now familiar with the main Semaphore concepts, we can take a look at what actually happens from the moment when you push your code to your Git repository until the first tests are run in Semaphore jobs. Now let's take a zoomed out look at what happens when you push your code to your Git repository. If you have seen the earlier presentation by my colleague Radoslav, this might be familiar to you. So, when you push to your Git repository, your Git provider will send a webhook to Semaphore, and it will arrive first to the part of the system called hooks processor. The hooks processor will validate and verify that webhook and transform it to a format suitable for internal processing. Next step in this process is called the pipeline processor, and this part of the system is the main focus of this presentation. There, we will fetch a YAML definition of that pipeline, create a pipeline based on that definition, and orchestrate the execution of blocks and jobs. The next part of the system is a job processor. It is responsible to prepare and manage execution of individual jobs on suitable agent machines. Finally, we have an agent pools in which the jobs are actually executed. Those are the fleets of machines that can be hosted by Semaphore or self-hosted by Semaphore users. Now that we are more familiar with the whole process, we can zoom in on the pipeline processing part and its main service called Plumber. We can start with defining the functional requirements. or what actually means to run a pipeline. In order to start a pipeline, we must first fetch a YAML definition of that pipeline, verify it, and process it. Next step is to validate conditions for running that pipeline and its blocks. The pipelines and blocks can be conditionally run based on criteria like the branch name or result of the previous pipeline in the workflow chain. Once the pipeline is cleared to run, the blocks need to be started in proper order based on their dependency graph. The jobs from each block are then passed to the next service and processing system. While jobs are running, the plumber is keeping track on execution time limits to prevent stuck jobs from incurring additional expenses. Also, if the user stops the pipeline manually, all running jobs need to be terminated properly. Finally, once pipeline is done, other services need to be notified. Now, let's see what are the non-functional requirements for the pipeline management system. The availability is the main non-functional requirement for the Plumber service. Our users rely on Semaphore to deliver their code, and any disturbances in the delivery system can have significant impact. The scalability of the system is equally important, especially during peak times when many developers are pushing their changes at a similar time. So the solution system also needs to be fault tolerant. So one malformed pipeline cannot stop the processing of all other pipelines from all other users. As the requirements evolve during the time, it is also important for a solution to be easily extensible to cover new use cases. Finally, there can be no false positives in the pipeline test results, since that can lead to our users delivering code with known issues. Now, let's see the architectural decisions we made when designing Plumber to cover these two sets of requirements. Architecture of the Plumber component closely follows overall architecture principles of the whole Semaphore. If you have watched the presentation from my colleague Radoslav, this will be familiar to you, but it still needs to be reiterated here in case someone missed that presentation. We are relying on microservice architecture since it allows us to develop and scale different parts of system independently. For deployment platform, we are using Kubernetes, and it allows us to seamlessly scale and update our services. The Plumber service is developed in Elixir programming language. Elixir is a modern language for functional programming built on top of the Erlang language from Ericsson Telecommunications Company. Both Elixir and Erlang have a built-in support for concurrency, distribution, and fault tolerance. For database, we are using PostgreSQL relational database as the main source of truth, since it allows us to keep the data consistent through atomic transactions. Finally, RabbitMQ is our messaging broker, and its primary function is to reliably publish messages to all interested microservices. When it comes to implementation, the Plumber was based on finite state machine mathematical model of computation. Per this model, the system can be in one of the finite number of states at any given time. The finite state machine system can change from one state to another in response to some event or input, and this change is called transition. If we check the example of a finite state machine system on the image on the right, we can see that there are three states: work, home, and bed. The arrows represent events that transition the system from one state into another, like taking a train from work to home or going to sleep in bed. This model is also a good fit for pipeline processing because pipeline's lifecycle can easily be mapped to a finite number of states with one starting and one final state. We can then implement a different worker to handle each specific state, which reduces complexity of the system. These workers can be triggered periodically or on outside signals, like specific job being finished. Here we see a simplified example of managing pipeline's lifecycle with state machine model. As previously, we have one starting state, and here we call it initializing state. When pipeline is created, it will start in this state, and here the worker will fetch the YAML configuration for that pipeline, process it, and create all needed subcomponents like blocks and jobs. The pipeline will then transition into the next state, called pending state, where the worker will validate the conditions for running that pipeline. If all conditions are satisfied, the pipeline will transition into the running state. Here, the execution of pipeline blocks and jobs will be orchestrated, and pipeline will remain in this state until all of its blocks are finished. Once all blocks are done, the pipeline will transition into the final state called done state, and the result attribute of the pipeline will be set to one of possible values, like passed, failed, or stopped. Now, let's take a closer look at the implementation of the worker process that will perform actions necessary for a specific state. Here is the simplified implementation of the worker in Elixir-based pseudocode. We are calling these workers loopers because they are looping through all pipelines in a specific state and executing them one by one. This worker is based on a Gen server, which is an Elixir abstraction over the process that receives and responds to messages. The Gen server will be the part of supervision tree, which is a mechanism in Elixir that ensures that any processes that crash are then restarted. When the worker starts or restarts, it will first execute the init function. This function will send the wake-up message to the same process with a configured delay. Once the message is received, it will trigger the handle wake-up message function. Inside this function, we will first perform the state-specific logic with doWork function, and then reschedule the next iteration of the work by sending another wake-up message. With this pattern, we get a worker that is periodically executing the state-specific logic. If we take a closer look at the doWork function, it consists of three steps. Firstly, we select one pipeline in the specific state and lock it by setting a flag in database. Next, we perform state-specific logic on that pipeline. This is the only part that is different between looper workers for different states. Finally, we transition the pipeline into the next state and unlock it by resetting its flag in database. Now, there is one problem with this approach, and that is what if something breaks in the state-specific logic step. As we said previously, the looper process will be restarted by Elixir supervision tree, but the particular pipeline will remain locked in database. To solve this problem, we can look at all pipelines that are being locked for longer than expected as being in the new stuck state. We can then implement the worker that will loop through all pipelines in this stuck state and try to recover them. As illustrated on this image, pipelines in all states except done state can end up in a stuck state. The stuck state worker will unlock those pipelines and return them into original state to retry the state-specific logic. If the original problem is still existing, the pipeline can end up in a loop between original state and stuck state. So we need to add a circuit breaker to transition the pipeline into done state after several failed attempts to recover and reprocess that pipeline. Now let's take a look at the implementation of this recovery worker. As we can see, the implementation of this worker looks very similar to regular looper workers for other states. We have an init function that schedules a work by sending a wake-up message with delay. Then we have a handle wake-up function that is executed once the wake-up message arrives, and it again executes state-specific work and then reschedules the next iteration. Finally, we have the doWork function, and here the main difference of the stuck state worker from other worker is. Here we will first find one stuck pipeline, and then based on the number of failed attempts to recover it, we will have two different behaviors. If pipeline was recovered less times than the limit, which is 5 in this example, we will transition it into original state after a back-off delay, and also increase the counter of recovery attempts. The back-off delay is increasing exponentially with each retry to allow enough time for resolution of any transitory issues that might have caused the pipeline to get stuck in the first place. On the other hand, if we have reached the limit of recovery attempts, the pipeline will be transitioned to done state and result attribute will be set to stuck. This approach allows Plumber to self-recover from any transitory issues, but also prevents the pipelines that are failing due to other issues from negatively affecting the rest of the Plumber functions. Now that we have seen how pipeline processing is working based on state machine model, let's see how that model allows us to easily extend functionality of the Plumber. Let's start with the simplified pipeline state model and examine how we would add the functionality of stopping a pipeline execution. User can stop a pipeline manually via API or UI action in any point of the pipeline execution. If this happens while pipeline is in initializing state, we can easily just transition it to the done state, since no jobs are yet running outside of Plumber. If pipeline is stopped while in pending state, the behavior is the same. We can just move the pipeline to the done state. But if pipeline is stopped while in running state, we have to first make sure that all running jobs are stopped before we can transition the pipeline to the done state. We can easily achieve this by introducing the new state called stopping state. When stopped in running state, the pipeline will send stop requests to all running jobs and transition into this new stopping state, where it will remain until all its jobs are done. After that, the pipeline can safely be moved to the done state with result attribute set to stopped. Now let's examine a different example of adding a new functionality to Plumber. We will again start from a simplified pipeline state model and consider how we would add pipeline queue functionality. Consider a case where a user pushes new commits several times in a row in a short amount of time. Each of those pushes will trigger a new pipeline, and if those pipelines are using any shared resources, then they should not be executed in parallel. Instead, they should be put into a queue and executed sequentially one after another. We can easily add this functionality by adding a new state called queuing state. We will modify the pending state to first check if any pipelines from earlier pushes to the same branch are already running. If there are no such earlier pipelines, the pipeline in question can transition directly into the running state as usual. On the other hand, if some earlier pipelines are already running, the pipeline will be transitioned into the new queuing state. In this state, the looper will check if all previous pipelines are done, and once that is true, it will move the pipeline to the running state. To conclude this presentation, let's recap how the Plumber implementation we have is solving all functional and non-functional requirements we defined at the beginning. For managing pipelines, we have a standardized solution based on finite state machine model, implemented and structured through the set of looper workers. The availability goal is achieved by relying on Elixir supervision tree to restart any failed workers, and Kubernetes liveness probes to restart any pods that have failed completely. In case of scalability, we can easily scale vertically by starting multiple Elixir looper workers within the same Kubernetes pod, and horizontally by adding more pods. For fault tolerance, we rely on built-in Elixir tooling like supervision tree and custom solutions like our workers that are handling Stack pipelines. And finally, for extensibility, we saw that we can easily extend the functionality by introducing new states into the pipeline finite state machine model. That would be all for today's presentation. If you are interested to learn more about the Plumber, all source code is open source on GitHub at semaphore.io/semaphore, so you can take a look there. If you have any questions, join us on our Discord server. Finally, if you have liked the presentation, consider subscribing to our YouTube channel to see if more interesting videos in the future. Thank you for your attention.
Hey, thanks for having me today at the Semaphore conference. I'm Sneha Wadhwa, a senior software engineer at Confluent, part of CP Build and Release team. I'm going to talk a little bit about what we do at Confluent and focus mostly on our Semaphore CI migration journey. Here's a quick agenda. I'll start by providing some organizational context, a brief introduction of what we do at Confluent. Then I'll take you through our journey of migrating the Confluent platform's build, package, and release pipelines from Jenkins to Semaphore. We'll dive into the key design choices that shaped this transition, the challenges we encountered, and how we tackled them. Most importantly, we'll look at the impact this migration has had on our overall processes. And then finally, I'll wrap up. So here we go. Confluent is a leader in building data streaming platform and is on a mission to set every company's data in motion. It was founded by the creators of Apache Kafka, which is an open source technology that has really become the industry standard for real-time data streaming. In fact, it's used by more than 75% of Fortune 500 companies. So, what does Confluent actually do? Confluent serves as the backbone, or you can think of it as a central nervous system for organizations, enabling seamless, continuous flow of data across systems. Now, what does this really mean? It means that businesses are no longer stuck with traditional batch processing, where they have to wait for data to be collected, processed, and acted upon. Instead, with Confluent, they can access, process, and react to information in real time as it happens. And that's a game changer. It allows companies to make faster, smarter, and data driven decisions. So, whether it's detecting fraud instantly, or powering real time analytics, or enabling seamless event driven architectures, Confluent provides the real time data infrastructure and platform. While Apache Kafka provides a powerful foundation for real time data streaming, but Confluent goes above and beyond by offering a fully managed enterprise grade platform, making it easier for businesses to harness the power of data streaming without the complexity of managing infrastructure. Now, when it comes to deployment, organizations have two choices. If they prefer cloud native experience, Confluent Cloud delivers a fully managed serverless Kafka solution, taking care of all the operational overhead. So teams can focus on building the software rather than maintaining infrastructure. Whereas for organizations that need more control and customizations, Confluent offers Confluent Platform, which is designed for self-managed environments. It provides advanced tools for security, monitoring, governance, and stream processing, making it ideal for enterprises that want to run Kafka on their own infrastructure. Confluent provide features like KSQL DB for stream processing, schema registry for data consistency. Then there's tiered storage for cost efficient scalability. And of course, security being a big concern for any enterprise. Confluent offers enterprise grade security with features like role based access control, ensuring organizations can securely stream data at scale. So at the end of the day, whether you need a fully managed cloud native experience or a self-managed solution with full control, Confluent gives you the best of both worlds. So you can focus on building real-time applications instead of worrying about infrastructure. Yeah, so if you haven't already, I would encourage you to visit our website to know more about Confluent offerings and solutions. And you can get started. Try out CP and Confluent Cloud for free. Now let's talk about our Semaphore migration journey. First of all, why did we migrate? Confluent has been using Semaphore for a few years now. Most of our Confluent Cloud workloads were already running on Semaphore. So we decided to migrate everything to a single unified CI system. The goal was to reduce maintenance work and improve the developer experience by having everything under one roof. Ultimately, we wanted a unified CI/CD platform for the entire company. No more managing multiple systems or dealing with complexities of having different tools across different teams. Now let's talk about the workflows we migrated. Last year, we focused on migrating our CP packaging and release pipelines. To give you a brief overview of what CP packaging involves, at a very high level, we build and package Confluent Platform CP components and then release them to our customers for on-prem deployments. But this isn't a simple process. It's actually pretty complex and involves more than 35 to 40 different pieces coming together. And since we are always working to keep our offerings up to date and competitive, we release frequently. These releases come in various forms, including major releases that happen annually, minor releases, they go mid-yearly, then we have patch releases which go every quarter, and of course, other monthly and hotfix releases as needed. Now, this migration itself wasn't an easy or simple task, especially given the size and complexity of our workflows. It took a lot of effort, careful planning, and coordination across teams. But in the end, it has finally paid off, making our processes more efficient and scalable. Next, we'll dive into the design principles that guided us through this migration. But before we get there, let's unbox CP packaging and take a closer look at its deliverables and the different packaging types we offer. So, Confluent platform is distributed in multiple forms. We have tarball archives that work with any operating system, making it platform agnostic. Then we have RPM and Debian packages for various Linux distributions, jar libraries for integration with Java-based systems, and we have Docker container images for those who prefer containerized deployments. All of these packages are available at packages.confluent.io, and the Docker images are published onto the Confluenting Docker Hub. Now, when it comes to our customers, they have a couple of options. They can either get the complete all-in-one CP package, which includes entire Confluent platform, or they can pick and choose one or more individual components like KSQL, schema registry, to plug and play into their existing Kafka clusters. So, whether they are looking for a solution or just specific components, we've got them covered. Yeah, while migrating our CP pipelines to Semaphore, we took this opportunity to revamp the design of our CP build and release workflows rather than just doing a plain lift and shift from Jenkins to Semaphore. In the next few slides, I'll take you through some of the key design principles that we applied and relied on throughout this migration. First one being modularization. What you see here on the slide is actually the old packaging pipeline we had in Jenkins. It includes multiple steps to build and package CP with 4 large and complex build stages for Debian, RPM, jar, and archive. Over time, these stages kept growing, adding more steps, and which eventually made the pipelines slower to run. I mean, just to let you know, a Confluent platform isn't just a single monolithic repo. Like I mentioned earlier, it consists of around 35 to 40 different components. We have to pull in code from various Git repositories, build each of the component, giving us jars, and then we finally bundle them into different OS native packages. So what we did here was decompose these massive Jenkins stages into smaller, more manageable and micro build blocks. This allowed us to modularize CP packaging process, making it more efficient and easier to manage. This is how our new CP packaging workflow look like. Although this is just a part of it, a subset of complete workflow. The key difference, it's now modular, as we can see. Instead of having large monolithic stages, we now build each CP component individually within its own Semaphore block. Then using dependencies between components, we have structured it as a DAG or pipeline in Semaphore terminology. We've leveraged Semaphore CI concepts of blocks, pipelines, and dependencies to achieve all of this. This eliminated the huge monolithic stages we had in Jenkins. Yeah, the next one, it's using Semaphore artifacts for caching. As we saw in the last slide, each CP component is built in a semaphore block, and then it's passed on to the next stage as a dependency. So we have to pass on the dependent jar to the next stage. So Semaphore CI provides a built-in support for caching and storing artifacts, and which has made all of this process much more efficient. We are using workflow artifacts to pass not only jars but other build outputs from one block to another within the pipeline. Also, to package CP, like I mentioned, we need to gather all 35 jars into one place, create RPM and Debian repository. So easy and fast way to do this is to use Semaphore artifacts, as it provides fast upload and download speeds, streamlining the entire process. Yep. So the next key design principle is maximizing parallelism. As you see in the screenshot, we have multiple blocks running parallelly wherever there are no dependency or when its dependencies are sorted. So, and within each task, we have jobs that also run parallelly. Each job is running in its own agent, isolated machine with a clean and fresh environment. Yeah, so we have both parallel blocks and parallel jobs. This has helped tremendously overall speedifying the CP packaging process. Another reason we modularized monolith stages in Jenkins into smaller build blocks was to improve debuggability. As you can see in the screenshot, in Jenkins, debugging failures meant scanning through huge pile of logs. Those are in MBs, and just because they were monolith stages, and which was very time consuming. But now, after decomposing and building each CP component in a different block, logs are now separated for each CP component, making it much more easier to identify and troubleshoot build failures. Okay, the next one is dynamic workflows. One of the limitation we encountered during this migration was that Semaphore workflows, including different blocks, dependencies, after pipeline jobs and promotions, they are all statically defined in its YAML configuration. This means we couldn't dynamically create blocks and tasks using loops, conditionals, and other programmatic logic. But for our CP releases, we needed workflows to be crafted and triggered dynamically based on given inputs. To solve this, we used Ginger templating, built a wrapper job that creates the semaphore workflow on the fly. This job will first generate the workflow dynamically based on the given release candidates we provide, and then it creates the workflow and triggers it automatically. So as you can see in the screenshot, workflows for package promotion, Docker image promotion, connector promotion, they are all created dynamically, stitched together in one workflow, and based on whatever input parameters we provide. And yeah, and then the release promotion is run. So this makes overall a workflow more flexible and extensible. The next one is use of promotions. The screenshot here shows our release workflow, like I mentioned. Instead of having one large pipeline, we have broken it down into logical promotion pipelines in Semaphore. These pipelines are automatically triggered when the previous pipeline succeeds. So this approach brings in two major benefits. The first one is parallel execution. Since independent pipelines don't have to wait onto each other, they can run in parallel. So it significantly reduces the overall release time. It also gives another benefit of better error handling. I mean, if a failure occurs, we can selectively rerun only the failed promotion pipeline instead of restarting the entire workflow. And as far as I know, Semaphore doesn't support rerunning only failed blocks within a workflow. But with the use of promotions, we have built a targeted retry mechanism, saving us hours when dealing with these sporadic failures. Another key improvement we introduced was defining the pass and fail hooks for each of the block and semaphore workflow. These hooks help us automate failure detection and notification. Here's how we leveraged them. As we see in the screenshot, firstly, it's Slack notifications. When a packaging build fails, an automatic alert is sent to the respective on-call team, ensuring immediate visibility and faster response times. Teams get real-time updates and they can jump into action right away. Secondly, Jira ticket creation. So a Jira ticket is automatically created and assigned in case of build failures. And ticket includes everything: build logs, semaphore workflow details, job links, everything in description, making it easy for engineers to quickly diagnose and fix the issue. This removes manual overhead of tracking failures and speeds up the resolution process. And lastly, we have matrix and dashboard. So to gain deeper insights, pass and fail matrix of each and every block, they are pushed onto matrix system and are being visualized in QuickSight dashboard. This allows us to track trends, analyze failures, and continuously improve our build reliability. Before this, debugging failures was very time consuming. Engineers had to spend at least 30 to 45 minutes scanning through massive logs just to identify which CP component had failed. Now, with this automated failure tracking, the mean time to detect has dropped from 30 minutes to 0 minutes. This has drastically reduced on call burden and operational overhead for engineers and has improved developer productivity. Yeah, like we saw, and given the complex nature of our packaging and release pipelines, we needed more than a regular CI/CD system. That is a workflow engine that supports manual job triggers and on-demand workflow execution, scheduled workflow execution, then parameterized workflows, and much more. So along the way, we requested a number of features to Semaphore team. Semaphore team was instrumental in supporting our journey by implementing many of them. Like we have built with like the task feature, then we have dynamic job matrix, parameterized promotions, etc. And few of the feature requests, they are still being in progress. They are being worked upon. Okay, enough of talking. Let's see the impact and results. They are pretty exciting. Um, Packaging builds, which were earlier taking 7.5 hours, they now take only 2.5 hours, and which is 70% faster. And yeah, so this is the build time reduction that we've achieved. And also, cherry on the top is that this is achieved by consuming 50% less resources, bringing in significant savings and infrastructure cost. Along with other benefits, of course, that we saw, that the pipeline is more modular, we have better UI, reduced on-call load, etc. But yeah, the build time reduction was the highlight. And here are the stats for our release pipelines. The release time of CP has been cut down from about 35 hours to just 8 hours. And this while shipping 8 different CP patch versions, which is almost 75% faster. Again, it's because there are lots of steps involved in release processes, like running malware scans, promoting OS native packages, Docker images, connectors, then doing a doc release, and so on. So combinedly, it takes around this much time. And all of these have been parallelized to speed things up. And plus, we did some major code enhancements and optimizations during this migration. Yeah, so that was another big achievement. And this is how our packaging and release workflows have been transformed. Need for speed was the main theme and the driving force behind this migration. Yeah. Virtual hi-fi and a big thank you to the Semaphore team for their incredible collaboration and support throughout this journey. Big thank you. Thanks a lot.
Hey there, my name is Kevin Ceballos, and today I'll be presenting on continuous improvement of our CI. So before we begin, let me introduce myself. I am a senior software engineer at SimplePractice. I joined in mid-2021, and I work on the platform team. This means I work on features such as authentication, fraud detection, CI/CD processes, that sort of thing. I've been in the industry for around 9 years now, working everywhere from small startups to large corporations. And in terms of what SimplePractice does, we are a health-based SaaS company that helps therapists, counselors, psychologists, etc. deal care to over 16 million people. Therapists use our platform to help manage their private practice. We currently have over 225,000 health practitioners on the platform. We've been around for a bit over 10 years now, and we are continuing to grow. Our tech stack is Ruby on Rails and Ember on the front end. Ruby on Rails on the back end, Ember on the front end. And in terms of how we use Semaphore, we run our test suite on most of our commits. Currently, we have around 55,000 plus backend tests. 51,000 of these are unit and integration tests. So these are generally quick to run. If we were to run it serially, it would take 3.2 hours. We have 4,000 end-to-end tests. We use Ruby on Rails on the back end. So Capybara is a library that helps us run those end-to-end browser tests. If we were to run these serially, it would take 4.8 hours. So a bit longer for not as many tests. These are notoriously our slower tests. And on the front end, we have 7,000 tests that would run 1 hour serially. We've also noticed that we have 3% growth in our test volume size month over month. So on average, every month, our test suite grows by 3% in terms of number of tests. And as you know, this compounds, and over time becomes quite large of a test suite. We use tools like Knapsack Pro to parallelize our builds. We chose this library because it plays well with Ruby-based tests and helps us split and load balance the tests across parallel nodes. And if you see above the graph there, above the chart, we run around 103 CI builds per day on all of our branches. So that's quite a lot. This is only for our main project too. We have other side projects that also have daily builds, but for our main project, we run around 103 CI builds a day. So it's quite a lot of machine time that we use to run all of our tests. Some motivations behind optimization and exploring optimization. So early 2024, we noticed that costs for our CI, monthly costs, were rising rapidly. We initially did not know why, and we were trying to figure out what were some first steps that we could take to diagnose. So we scheduled a bi-weekly meeting with Semaphore and their team to help diagnose and explore potential solutions. We also started a cross-org communication channel on Slack so that we could communicate across time zones. This has proved pretty helpful for us for ad hoc questions that may pop up. And we also performed a detailed audit of each step in our CI process just to find problematic steps that are running too long, longer than expected, areas that we can optimize. So some of the key problems we identified throughout the initial stages of the optimization process were ballooning CI costs. This was shown in the monthly billing. Inefficient CI utilization. During our audit, we discovered that certain areas were not efficiently using caching or being parallelized. And number 3, we had a lot of flaky tests. So flaky tests, if you're not familiar, are tests that pass some of the time, but other times they do not pass. This could be like time zone related issues, async behavior, stuff like that. We've noticed flaky tests are more prevalent in our end-to-end capybara tests. So yeah, these were the 3 main issues that we identified and we developed a plan to address. So when we did our audit, we also found several key problems that guided us in our approach. First off, we noticed non-optimal caching of the front-end build. We also noticed that the front-end build step was duplicated across all of our parallel nodes, which is a no-no. You want front-end to only build once, and then you in your parallel nodes you can pull down that build and run your tests. As much as possible, you want to decrease work that is repeated in those parallel nodes just to save yourself build time. Another key finding, we found that a front-end library upgrade a couple months before our investigation drastically increased build time. This was a bit hard to pinpoint. We had to basically trace the commit history to try to find the commit that caused an increase in the front-end build time. We also found and noticed that the entire CI runs on every push, even for like draft PR. So if someone were to push a draft PR and push daily, update commits, work in progress commits, those unnecessarily ran our entire CI. So we tried to think about ways we could avoid that or make the process run the CI build less. And finally, as I mentioned, flaky tests were causing a lot of CI reruns and retries. If you have a process or a rule in your organization to not merge failing builds, you could imagine how disruptive a flaky test would be. So engineers were often retrying their entire CI build to try to get to a green state. And that was obviously causing us to eat up a lot of machine time for our CI, which results in increased costs. So what was our plan of action to address these issues? We had some short-term initiatives and some long-term initiatives. For the short-term initiatives, we decided to upgrade the front-end build libraries. As I may have mentioned before, we had one problematic library that had a negative impact on the front end build times. It caused it to increase drastically. So once we were able to find that library, we upgraded it to a more recent version, and the issues seemed to go away. We also explored, other libraries, front-end libraries, to see whether there were any other ones that we could upgrade and increase the build time. We also made some optimizations to when we actually run the CI. For example, we chose to implement a policy where we don't run the CI on draft PRs. We just skip it. Developers could get around this by manually including a commit message to trigger the CI, but for the most part, it was skipped during draft PRs. We also split up the test suite to fail fast on unit and integration tests. As we've noticed, the unit and integration tests are the ones that run fairly quickly relative to our end-to-end tests. So if we were to split our CI into multiple stages and fail fast on the unit and integration stages before we even think about executing the end-to-end tests, then that could save us quite a bit of time, since we don't need to really run the end-to-end tests until the first phase passes. And this is helpful in those cases where an engineer pushes up a PR that has some bugs in it. Those unit and integration tests fail because they catch the bug, and then the engineer addresses those failing specs and the bug, and then hopefully then the PR is ready to run the entire test suite. So failing fast basically saves you runtime by not executing the entire test suite every single time. We found the granularity of failing fast on any one step to be too granular, so we decided to fail fast instead on the entire unit and integration block instead of one failing test. So basically, we run the entire unit and integration block, and we report all the failed tests within that block. Once all those pass, we move on to the end-to-end tests. We also utilize the change-in feature in Semaphore to only run front-end tests when the front-end has changed. So thankfully, our file structure has a separate front-end directory, and that's where all of our front-end code lives. So we were able to use the change-in feature provided by Semaphore in our CI YAML file to specify that we only want to run our front-end tests when anything in the front-end folder or directory has changed. So this actually optimized our test suite by conditionally running those front-end tests, and it helped quite a bit. We also decided to build our front end and our back end once in a parent step, upload it to the Semaphore cache, and then pull down the cache in parallel nodes. This is to prevent each node building the app, which it did for the front end in early 2024. So we addressed that, and we also, to try to address the flaky test problem, we established a new process to quarantine, remove, and resolve those flaky tests. Over the course of last year, we identified and removed around 83 flaky tests. Semaphore actually provides a useful tool. I don't know if it's still in beta, but provide a useful tab within your test insights to identify flaky tests. So we've used that to try to identify tests that have failed on the same commit, I believe. We also try to shift our testing culture to prioritize unit and integration tests over end-to-end tests, as unit and integration tend to run faster and are less flaky. We also tell engineers to try to use the skip CI commit message more often when they don't need to run the entire test suite. For example, if they're just pushing up their code for the day and going home. This next bullet point kind of ties into a longer term initiative that we addressed. So we eventually Dockerized the app for our CI. We had a Docker image, built for deployments, but in our CI we were just setting up the app sort of within the base CI container. And we weren't using any Docker images there, but we decided to go forward and Dockerize the image for CI purposes as well, so that we could build the front end and back end, upload an image on a parent CI step, and then pull it down for all the parallel nodes. And to help with this, we also use the Semaphore container registry. Initially, we were using AWS. We noticed we were paying quite a bit in network costs, so we switched over to the Semaphore container registry to save on costs there on network traffic. And finally, our last long-term initiative was to switch to a different front-end build tool. For the longest time, we were using Broccoli, which is a build tool in Ember that is sort of the default one quite a few years ago. But Embroider is a more recent build tool that has a lot of performance improvements and helped us quite a bit in terms of reducing our front-end build time. So yeah, that's a brief summary of all the different actions that we initially took in early mid 2024. All of these we also addressed by the end of the year. And yeah, this next slide sort of shows some of the month-over-month percentage change in costs improvements that we saw. The star here on the chart is the month that we met with Semaphore and we started sort of optimizing. This was in April of last year. As you can see, the month after that, we had a drastic drop in costs because we were able to identify some quick wins and areas that we could immediately optimize. There were some spikes in July and October. These are just some small issues. For example, in one instance, we may have left a cron job to run specs on that sort of increased cost, and I would consider them anomalies. But in general, the general trend is that the costs have decreased. And something to note, our team size has increased during this period of time, and also our tests have increased 3% month over month over this time. So overall, we're still we dropped in price in month over month costs over this time, despite having growing team and growing test size. Some future steps, optimization is a continuous sort of cycle. We don't expect it to ever stop. There's always going to be some improvement, some new advancement in technology that will help us optimize further, make our test suite run faster, that sort of thing. So we're always, continually trying to improve there. We also have to keep in mind that CI optimizations, we need to balance that with more impactful work in our org and company priorities. As many of you may know, CI work is probably not at the top of the priorities for most companies. They until they start to see costs rise. For the most part, they like to focus on product focused, features. So consider the opportunity cost of your optimizations and whether it's worth optimizing at your current scale. For example, you don't want to over-optimize when your test suite is still super small. For example, like you don't want to spend or waste a month trying to investigate an optimization that will only save you guys hundreds of dollars. And it may make more sense to wait until your month could be dedicated to solving a problem that can save you guys thousands of dollars over the course of a couple months. So try to evaluate whether it's worth optimizing and which sort of things you optimize. Further steps, we want to explore using Cuprite. I hope I'm pronouncing that correctly. This is a Ruby sort of tool, Ruby-based tool that I believe moves away from using Selenium for our end-to-end tests and uses the headless browser. People have noted that there's quite a bit of a speed up that they experience when switching to Cuprite over the default Selenium WebDriver that most Capybara setups are set up with. So we are exploring that. We're also exploring using Datadog's test impact analysis tool. So this tool is supposed to help you conditionally run your unit tests based on files that have changed. So let's say you have a PR up that changes 4 Ruby files. This tool would only run the tests that those 4 Ruby files impact. It seems very promising. We haven't actually dedicated that much time into implementing and investigating this tool, but if it works, then that would also save us a lot of CI runtime. And finally, we are exploring only running our slower and flakier end-to-end tests only before release. So we are essentially some orgs do this, and it's not too conventional, but maybe once you get to a certain size, it starts to make sense. We only want to run the end-to-end tests on our release branch right before release to make sure that those tests pass there. This would be in contrast to running them in every single PR and every single commit that is pushed. So to summarize, we are continuing to iterate and optimize. We're trying to maintain a stable cost relative to the team and test suite size and growth. And we acknowledge that there are always going to be unavoidable sequential workloads that we can't parallelize, and we must be strategic in the areas we try to optimize. There's a sort of law for this called Amdahl's law, I believe, where there's a formula basically that tries to guide you in, what areas you should optimize and what areas you should parallelize. And this formula actually takes into account the fact that there's unavoidable sequential workloads that you'll always face. So yeah, I just wanted to end this presentation there. Thanks so much for your time. Thank you.